Yeah, I didn't bring your in. Okay.
It's like a quick.
Thank you.
No.
And we're not letting anyone else after your cookies are gonna be better. I'll make mine first on purpose.
It's too popular.
Oh, thank you. Doing great already. I appreciate it.
Family ones.
Of course. It's open to the public. Yeah, that's why you announce. Anyway. That's good.
It's all on your body.
I'm good. I guess we're waiting for MARL for now. Yeah.
I have a selfie.
Depends. Thank you so much.
Sure. Family last. How long it's gonna be?
Depends.
No, I wouldn't invite him. Look, he hasn't ready.
Already know. Yeah.
All right. Hello, everyone. Welcome. So today we have one of our graduate students defending their master's thesis, Hamid. So he joined us 2021.
Right.
Yes. September 2021, and he has been working on two projects. One was strong with a lot of you guys here, and thank you to all. Mostly on the stuff that is going to present, and then he worked on a different project, NSF M3X, which is focused on exoskeleton control and learning. That research related to that is not in this presentation, but is things that he published on and is just on its own worth a thesis. So we didn't want to have two different topics for a thesis, so we just went with the one that we like more. I would like to thank the committee for taking the time and agreeing to be doing this service. And if you're ready, I think the plan will be We go about 40 to 45 minutes of the presentation, and then we open to questions from the public. Anyone can ask questions, 5 to 10 minutes. And then the public will leave, the candidate will stay with the committee will ask questions. And then we let Hamid go, the committee decides on their consensus, and then we call him back and tell him the results. So this is the structure for any master and PhD thesis. So Hamid, if you're ready, I don't know how many people are on Zoom, but
we have 2 people on the Zoom.
okay.
Yeah. Thank you so much for that great introduction. That made my life easier because I do not need to go through all that. So today I have the pleasure to present my work on a multi-robot task assignment framework for search and rescue with heterogeneous teams. So I'll go through the importance of search and rescue, why we are using robots, and the importance of task assignment. And in the end, I hope that you know more about all these terms here. Okay. Why do we use robots for search and rescue? Okay. It happens. The YouTube video is not running. By the way, this was a video from the Center for Robot Assisted Search and Rescue. They are, I guess, one of the few places that use robots in real-time search and rescue. The very first time that robots were used towards this goal was after 9/11 attacks. Robots can navigate debris and rubble after a disaster. They can enter like narrow cracks and do what is not possible by humans. So it is useful to use robots for search and rescue. Okay, I guess the sound was playing somewhere, but it wasn't.
There is someone in Zoom.
Okay. I can see that. Okay. So if the team of robots that we are going to use for search and rescue are all the same, and we have, in other words, a homogeneous team of robots, it will be easy to assign different tasks and do a search and rescue mission. However, this is the actual set of robots that were used after 9/11 attacks. You see, each one has different capabilities. So some of them have manipulators, some have like a specific kind of wheels. So they are different in terms of capabilities, and they should be used differently to optimize the overall mission. Also, time is super important in search and rescue missions, because after 48 hours of a disaster, number of alive victims decreases significantly. So then to overcome this issue in terms of time and in terms of being efficient for planning, we proposed a comprehensive multi-agent task assignment framework that includes a scouting step in which a set of robots are sent and provide the information about the location and the requirements of the victims. And then we use that information to assign the tasks to robots with different capabilities, or a heterogeneous team of robots, like what we had in that black and white photo. And finally, we use path planning to send the robots to each of those locations for each of those tasks. For the first part, which is scouting, we propose an environment for multi-agent reinforcement learning, specifically for search and rescue. This work was inspired by work by Ming Tan in 1993. And we define a limited visual field for the robot, which is very realistic. And the robot starts searching the environment. And if the victim is within the visual field, the rescuer robot, the green agent here, learns to go towards the victim. And if the robot goes to the same cell as the victim, the task will be finished and the information will be provided. To enhance this work, we have another agent in orange, which is a scouting agent. The scouting agent just searches the environment, and if it sees a victim, the information will be sent to the rescuer agent. And because the rescuer agent always knows the location of the scout agent, it will be able to calculate the location of victim. To have a feeling about the effect of adding a scout, because when we define a rescuer agent or a scout agent, and we want to train this in reinforcement learning, the observation space for the agent will be all these cells, plus one more cell for search. So here it is 3 by 3, 9, and one more will be 10. But when we add a scout, specifically in a large environment, which is like in this case was 6 by, we had a 5 by 5 in this example. But the larger the environment, the larger the size of the observation vector. And this is what happens after adding a scout, because we will be able to see the victim anywhere in the map. So the observation space increases significantly, which makes training very expensive computationally. We also extended this environment to a scenario that the agents can search the environment, find the victims, pick them up, and put them down in a master site. For that one, this observation space will be doubled because we need another one for getting the victims to the master site. Throughout this work, we have used independent Q-learning to train the agents, but the environment and the open source code also includes distributed Q-learning and DQN versions. Within this scouting framework, we also propose a game theory framework that proposes action suggestion to improve the scouting. Game theory is a field that studies the interaction between the agents. So on a case of non-cooperative agents, there is a security level defined for the agents. So if you are non-cooperative and I want to minimize the cost, I should consider the worst case by my teammate, which is not my teammate, it's my opponent when it's non-cooperative. Yeah. So if it selects the maximum cost, I should minimize on that. And this way, I can select the best action, whatever the teammates, the opponent's action will be. And this is an example of prisoner's dilemma in which two prisoners want to get detained for fewer number of years without even knowing what is going to be, what is the act of their teammate is going to be. Because we have different agents that are being trained in the same environment and they have their own Q tables, we said, okay, if they suggest actions to each other, because they have been in the same situation before, the situation or the cell or the estate that their teammate is, we can run a game between them. And I will show you the results for all the scouting experiments, I mean the evaluation of the scouting and this game theory framework as well. Okay, the main contribution of this thesis is the task assignment framework that uses market-based and optimization-based methods to combine the good points, the strengths of both areas. It has 6 steps, and I will go through all of the steps and will define each step for you. After the scouting step, as I said, we have the information about the location and the requirements of the victim. I will use a super simplified example of 10 victims with some random requirements that I use some names for them, and a team of 4 robots that have different capabilities to define how this task assignment framework is working. However, this can be used on any, this is generic. It can be used on any example, but this is, as I said, as a super simplified example to define or describe the performance. Okay, we have the information about the location and the requirements, and we define a theta vector for the victims, which is simply a binary vector showing which requirements from the list this victim requires, and a row vector which says which requirements the rescue team robots have. The first step is requirement and capability analysis. So we have that information. We can do the analysis and provide 2 lists on each side. On the victim side, we provide a list that says, okay, potentially each of these requirements can be satisfied by which robot. Like the second requirements of victim 0 can be only satisfied by robot 0. And we also define a list of unavailable requirements of the victims, because there might be some requirements that are not available in the list of robots in the rescue team. So we will need some backup or support team. On the robot side, we also define 2 lists, a list of requirements that this robot that can fully satisfy. I mean, robot 0 can satisfy all the requirements of victim 8. And also a list of requirements that can be partially satisfied. I mean, robot 0 will satisfy part of the requirements of victim 4 or 2. Why are we doing this? After this, we can we had to set some information, location and requirements of the victims. We use the requirements, and based on the location, we can categorize the victims in different clusters. We use k-means clustering, but here again, any method can be used for clustering. And we also considered because there are walls in the environment, and there might be victims that are in the same cluster when we use clustering based on location, but they are on the 2 different sides of the wall. So if we send a robot to give service to both of them, it will be a long journey. We do a comparison with an empty map, and we calculate the Manhattan distance with the path planning that method we are using, A* in this case. And if the distance in the map with walls is longer than the map, the empty map, we conclude that there are walls, and we remove those victims that are far from the cluster center from that cluster. The red C values here are the cluster centers. After this clustering, our first set of assignment starts, and we assign clusters of victims with requirements to the robots. And robots travel to those cluster centers and start giving service to the nearest victims. To do this, using those 2 lists of partial and full satisfaction of the requirements, we define 2 weights, which is W for this robot in this cluster for partially satisfying those requirements or for fully satisfying a requirement. And we use linear optimization or linear assignment to formulate it. And we also define a prioritization coefficient. Why? Because we can use this coefficient to prioritize giving service to the victims whose requirements can be fully satisfied by the robots in comparison to those who can be partially satisfied. So here we use the 0.95. So it will be prioritized for fully satisfying the requirements. After this first step, we see that robot 0 is assigned with cluster 1 and robot 3 is assigned with cluster 0. This step is not the best one for all the robots, so there's nothing assigned to robots 1 and 2. So after the first step of performance, we can measure the performance of the robots and allocate the remaining victims again to these robots. We use a similar formulation and the recorded time of succeeding on the task and failure over the task. And for sure, we want to decrease this time. As I said, time is super important in search and rescue. And here, the prioritization coefficient will help us to focus on the failure time. That's the one that we want to decrease for the most part. And this step will also assign some victims to some robots. There will be still requirements for some victims in the environment after these two steps of optimization. As I said, our approach uses optimization and market-based approaches. For the last part, most of the previous contributions use the same optimization several times to finish the whole mission. However, as I said, there are pros and cons for each one. One of the shortcomings of optimization-based methods is that they are computationally expensive and they increase the overall planning time. For the last step, we used a market-based approach in which each robot with those capabilities proposes its distance to the remaining requirements, and we want to minimize that distance. So simply said, the nearest robot with that capability for that requirement will be sent to the remaining requirements, and this will finalize the task assignment framework for us. And after these two steps, we simply use path planning to send the robots to each of the victims one by one. And as I said, we use A star, but there can be like Bellman-Ford or whatever. Okay, this was the overall framework and the description of what we have done. From now on, I will present the results of each section. We evaluated the search and rescue environment by training each agent with Q-learning. We worked on, wait a second. I will present results for the entire episode and sometimes for the time that the victim is being seen by the rescuer or a scout. Also, to ensure robustness, we present the results for 100 runs, and the result is for average of those 100 runs, and there is also a standard deviation shown on this. We evaluate the environment for victims' speed, a scout's visual field size, and team structure, having 1 or 2 scouts and communication with them, and the number of scouts. The first one is the victim's speed. We see that the yellow one converges later in comparison to the 2 others. The yellow is for a fixed victim, and the red one is for a but the pink and blue are for normal and a slow victim. Normal victim means it takes one step at a time, similar to the rescuer, and a slow means it takes one step every other step that the rescuer is taking. Because when, as I said, this is an average of 100 experiments, when a victim is fixed on the environment, we should spend more time exploring the environment to find it in comparison to an agent, in comparison to a victim who's running or walking in the environment. Chances will be higher to see them. And we also do a comparison for the time. That was for the entire episode, from the beginning to the end. But this is for the time that the agent is being seen by the rescuer. So we see that saving a fixed victim or a slow victim is kind of easier because that takes shorter time to converge in comparison to a normal speed victim. That's because if you are seeing a victim within your visual field and it stays there, you can simply go to find it. But if the victim is moving, it might get out of your visual field sometimes, and this will increase your overall time. From the scouting point of view, there is also the same. And we see that for the fixed victim, there is a fluctuation of the results, because if the rescuer gets to the same cell as the victim is saved. The episode is finished. The training is finished. But for the scout tries to follow the victim and send back the information to the rescuer. So if it is fixed, because our scout doesn't have the idle action to stay in the same cell, it will have to go back and forth from to that cell, and it will fluctuate the results. You see the yellow and blue one is fluctuating here. Okay, after victim's speed, we also do a comparison on the scouts, the size of the visual field for the scout, for sure. A more capable scout with a larger visual field, I mean, will improve the performance of the rescuer. This is the result of this section. And then we have a scout with a visual field of size 4. The rescuer gets more reward overall in comparison to the time that the size of the visual field for the scout is 3 or 2. The scout sees more cells, the chances of seeing a victim and sending the information increases. So that improves the performance of the scout. Finally, we discuss the team structure. If we have, up to here, we had one rescuer, one scout in the environment. What if we have 2 rescuers and 2 scouts, or no scouts? And for the 2 scouts, what if each rescuer just communicates to one scout or to both scouts? We see that communication to no scouts is results in a worse performance for the rescuer, and communicating to more number of scouts improves the performance. By the way, in this grid world environment, discretized environment, having access to the information of 2 scouts in comparison to 1 scout is not, I mean, is not significantly different. You see, they are almost on the same line. However, this was very interesting. If we check for the time that the victim is within the visual field of the rescuer, we see that having access to no scouts is better. Why is that the case? Because if we have the information of the victim within our visual field, it means it's a maximum of 1 or 2. The size of the visual field here for the rescuer is 3. So it will be 3 steps away. But if the scout is providing the information, that will be much farther, somewhere else in the environment. So if we consider the time that the information is available, it will be easier to save someone within our visual field. So that is why without scouts, we get more rewards overall. For the last part, we did a comparison in the 10 by 10 grid world environment on the number of scouts. What number of scouts is enough for the rescuer to have its optimal performance, its maximum reward is being attained. So we started with 1 rescuer to 10 scouts, from 1 to 10 scouts, and we see that somewhere around 5 scouts, the dark blue one, the performance is almost the same, which means more than 5 scouts in a 10 by 10 grid world is unnecessary for a rescuer in this scenario. And this is the result for the game theory framework. If we use action suggestion, as we mentioned by game theory, and do a comparison between the time it takes for the agents to converge on that behavior and task, in the game theory scenario, it will take about 80 steps. But if there is no communication between agents, it will be much larger, like 234 steps. So we have a significant decrease in the convergence time by about 66% when we use the action suggestion by game theory. And also, if the agents, even if the agents are communicating, action suggestion works better. And we see that it will be 193 steps in comparison to 80 steps, which is about 58% of improvement in convergence time. Okay, the results for the task assignment are provided for 4 different maps. And to ensure the scalability, we use teams of 2 to 10 robots for the task assignment when we have 10 to 100 victims. And this is an average on 100 runs. We see that we do a comparison to a baseline algorithm by a 2020 paper by Carreno et al. And we see that by that baseline algorithm, the planning time is somewhere between 0 and 10, but ours is between 0 and 0.14. For map 0, which is an empty map, for this map 1, it is for the baseline, it is always between 0 and 10. But in our case here also it decreases to from 0 to 0.06. Map 2, the same, decreases to 0.12, and map 3 decreases to 0.055. On average, our approach has 97% improvement in comparison over the planning time in comparison to the baseline. As a future work, as I said, all these experiments with were in a grid world, a discretized environment. As a future work, this can be increased to a continuous environment. Okay. This was formulated as a single objective optimization problem, but it can be also formulated as multi-objective optimization. And there can be real-world experiments using fleets of mobile and flying robots. Okay. And here is a list of my publications. The first two with field bullet points are relevant publications, and the rest are my publications during my time here. And in the end, I should say a big thank you to everyone who supported me during this time, especially Dr. Reza Azadeh for his support, his passion of teaching, and also the team on a strong project, the PIs, Dr. Duras, Dr. Robinet, and also again Dr. Azadeh, and my nice committee members and all the friends who made this journey easier for me. Thank you so much.
All right, thank you. Question?
So, we're going backwards order. So if you go to the planning time for your framework that you're suggesting,
Okay.
so the baseline, as you get more robots, the planning time increases. That makes sense. For yours, do you know why 2 or 3 robots would be like the worst planning time? Like, I know it's small differences, but you know, it seems like as you get more robots, your planning time decreases, which is counterintuitive.
Yeah. When the number of robots increases, the planning time also increases. I mean, with our experiment, with our framework, the planning time is prone to the number of robots.
Yeah.
I guess that's because the planning time is decreased to a fraction of time, and there will be more fluctuations, but the baseline has always the same like interval for all the assignments.
Okay. It was just random.
Yeah,
Worked out that way.
this work was published in a workshop in IRAS 2023, and in that paper we point out how much decrease this causes.
I see. I have one more question. So back when you were doing the clustering,
Mhm.
you did this thing where you cluster it, and then if it's across a wall, you like put it into a different cluster, right?
No, I just remove victims from that cluster,
Yeah.
and that will result in the first step to be ignored. I mean,
okay.
you saw there were 2 robots that were with no clusters assigned to them.
Okay.
That
so
was
that
one
is
of the
not-
results. Yeah.
Oh, okay.
We will go to the next step.
I see. All right. Thank you. That's my short question. It's not that hard questions, I feel like. I think he answered them.
Other questions?
I can ask one. Sorry if I'm,
No, that's
my question sound does not right. Pardon me,
okay.
but it was good, very good presentation.
Thank you so much.
And my question is that when you're applying the Scout algorithm,
Mhm.
so have you considered the impact of where you are initializing the Scout robots, like at the top of the room or at the bottom of the room or the corner of the room, like?
The results presented here are for 100 different runs. On
Mhm.
each of those runs, the initial location is randomized in the environment.
Okay.
So each time it will be in a different location, and the formulation is based on the relevant distance to the goal.
Okay.
I mean, if it is within the visual field, we know the relevant distance, and it will be one of those cells within our observation vector. If it's not, we will just be in search mode, and we'll use some search algorithm. Here we used ant colony search algorithm, but it can be also other search algorithm like random walk or whatever.
Thank you.
Sure.
I apologize if
That's-
you said this and I had missed it, but do you have a contingency for what happens when one of the scout robots has a disconnect with one of your ground ones? Like if they lose communication, is there a contingency for that, or? I know you have the framework for none, the no scouts, but what happens if all of a sudden, like, because in a real world situation,
Yeah.
there's communication.
That's an interesting question. We didn't work on that side. I guess you mean if at some point within the training, the information from the scouts will be blocked somehow.
Yeah.
I guess it affects the training behavior. The performance will decrease significantly at that point because up to now we could see everywhere in the environment, but now we are seeing it within our visual field. That should be repeated several times because in one experiment that might be the time that the victim is within our visual field, so nothing happens. But if the victim is outside our visual field and we lose information from the scout, that will be an important issue.
How many grid boards, grid cells are covered in the field of view of each scout?
Depends on each experiment. It was somewhere between 1 to 3. Like this one has, I mean, the size of the visual field. The size is 3 here, which means 3 cells away.
That's front, right?
No, all around.
Okay, so it will be 3 by 3. It will
Ye-
be 9.
5 by 5.
No,
5 by
It-
5.
it's feel-
Oh,
yeah.
Okay.
I should have.
So if it is 5 by 5, give me a second here. If it is, I'm worse than him.
No.
If it is 5 by 5, it's 25. Then your grid board was 10 by 10, which is 100. And you said 10 scouts, like each of them is covering 25, then 4 should be enough. But
I see. What I didn't mention here was the formula for calculating the observation space from the visual field. When we say a scout has a visual field of 3, the size of the observation space will be 2 times 3 plus 1 to the power of 2. So a visual field of 3 means a 6 by 6 environment will be seen by this scout. 2 multiplied by 3 plus 1. Okay.
no, I got that. I'm saying, so if the whole environment is 10 by 10, right? It's a grid board. I can ask that question
No.
later. Leave it.
I see what you mean. You mean.
I know.
Let me get back here. The size of the scout's visual field is 2 here.
Okay,
Okay.
that makes sense. No,
So
that
it
makes
will be a
sense.
5 by 5 and within a 10 by 10.
All right. There's other questions? Not all. If not, I ask everyone, thank you again.
It's like the tomorrow. We're giving the pizza, so say whatever you want.
Yeah. All need to go.
Should I stop the recording?
Yeah.
Okay.
And keep people out of Zoom.